Find somewhere comfortable. You don't need to follow any of this closely. You don't need to hold on to a single word. Just let the sounds arrive the way distant rain arrives, not demanding anything, simply there. If you drift before we've gone very far, that's a good thing. That's exactly the right thing. Tonight we're going to move through one of the quietest ideas in all of science. An idea so strange and yet so thoroughly proven that it changes what it means to exist in this universe. We are going to talk about time. Not time as a pressure, not time as something running out. Time as something soft and yielding. Something that bends. You might be tired tonight. You might be carrying something heavy from the day. A conversation that went wrong. A worry that has followed you to bed. The particular ache that comes from simply being a person in the world. Whatever it is, you can set it down. The night is patient. The universe has been here for nearly 14 billion years, and it is in absolutely no hurry. So rest your weight into whatever is beneath you. Let your eyes close or let them go soft. We'll begin at the beginning, not with equations, not with anything you need to concentrate on. Just a quiet story about how the world turned out to be far stranger and far more beautiful than anyone expected. For most of human history, time was the one thing everyone agreed on. Not politics, not religion, not the shape of the earth or the movement of the stars, but time. Time was the great constant. The river that carried all things equally, flowing at the same rate in a farmer's field as in a philosopher's study. The same in London as in Shanghai, the same on the surface of the earth as somewhere out among the stars. Whatever else was uncertain, time was not. It was the stage on which everything else happened, and the stage everyone assumed did not move. It was a reasonable assumption. It felt true. Every clock you wound, every heartbeat you counted, every shadow you watched cross a sundial, all of it suggested that time was simply there, ticking away behind the world like the mechanism behind a painting, invisible and perfectly steady. Even the greatest scientists of the 17th and 18th centuries built their entire understanding of the universe on this foundation. The universe was a vast, precise machine, and time was its metronome. The first quiet crack in that assumption did not come from a philosopher or a dreamer. It came from a Scottish physicist named James Clerk Maxwell, working in the mid-19th century surrounded by coils of wire and the smell of chalk. Maxwell was interested in electricity and magnetism, two forces that had seemed entirely separate until he began to suspect they were two expressions of a single, deeper thing. In the 1860s, he gathered together everything that was known about electricity and magnetism and pressed it into a set of elegant mathematical relationships. And from those relationships, almost as a byproduct, something extraordinary fell out. Light, Maxwell realized, was an electromagnetic wave, a ripple in the fabric of electric and magnetic fields propagating outward through space. And his equations told him something specific and strange about that ripple. It always traveled at the same speed. Not approximately the same speed. Exactly the same speed, always, in a vacuum, roughly 300,000 kilometers every second, a number so large it barely fits the imagination. That is fast enough to circle the Earth more than 7 times in a single second. But here was the strangeness. Every other kind of speed we know is relative. If you throw a ball from a moving train, the ball's speed is the sum of your throwing speed and the train's speed. That is simply how speeds combine. Everyone understood that. And so the natural question was, relative to what was light traveling at this constant speed? The sound of a bell travels relative to the air around it. If you move toward the bell, the sound reaches you faster. Surely light was the same. Surely there was some medium through which light propagated, and light's speed was measured against that medium. This hypothetical medium was given a name, the luminiferous aether. It was imagined as a kind of invisible substance filling all of space, perfectly still, the ocean through which light swam. It had to exist. Without it, the constancy of light's speed made no sense. And if it existed, then the Earth, moving through it on its orbit around the Sun, would create a kind of ether wind, the way a cyclist feels wind even on a still day, simply because they are moving through the air. Light sent in the direction of that wind should travel at a slightly different speed than light sent against it or across it. In 1887, two American physicists decided to measure that difference. Albert Michelson and Edward Morley built a device of remarkable delicacy, an interferometer, a machine that splits a beam of light into two perpendicular paths, bounces each path off a mirror, and then recombines them. If the two beams had traveled at even slightly different speeds due to the ether wind, the recombined light would show a characteristic pattern of interference, the two waves slightly out of step with each other, like two ripples on a pond meeting at a slight offset. Michelson and Morley floated their device on a pool of liquid mercury to isolate it from vibration, and they turned it slowly, watching for any change in the interference pattern as the arms rotated relative to the supposed direction of Earth's motion. They found nothing, no shift at all. The speed of light was the same in every direction, regardless of how the apparatus was oriented, regardless of the Earth's motion through space. This result was deeply unwelcome. It didn't fit anything. Michelson himself reportedly described it as a failure. The experiment had been designed to find something, and it found nothing, and the nothing was worse than any something could have been, because it left science without a story. The aether theory limped on for nearly 2 more decades, patched and adjusted by various physicists trying to make it work, but the patches never quite held. The null result, the absence of any difference, sat at the center of physics like a splinter that couldn't be removed. Then, in 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that did not patch the problem but dissolved it entirely. Albert Einstein simply accepted what the Michelson-Morley result implied. The speed of light is the same for every observer, always, regardless of how fast they are moving. Not because of any medium, not because of any special property of the apparatus, just because that is the nature of light. But Einstein didn't stop there. He asked a question that no one else had thought to ask in quite that way. He asked, if I were somehow riding alongside a beam of light traveling at exactly the same speed, what would I see? Would the light appear to stand still beside me, the way a train on a parallel track appears to stand still when both trains are moving at the same speed? The answer, he realized, was no. You could never see light standing still, because no matter how fast you moved, light would still race away from you at the same speed. And if that was true, if the speed of light was truly constant for every observer no matter what, then something else had to give. Something had to be flexible enough to keep that constancy intact. And the thing that gave, the thing that bent and stretched to accommodate the absolute fixity of light speed, was time itself. The clock that everyone had assumed was ticking steadily behind the universe turned out to be nothing of the sort. It turned out that every observer carries their own clock, and those clocks do not agree with one another. They never did. We simply hadn't been moving fast enough or measuring precisely enough to notice. Imagine a clock unlike any you've seen. 2 small mirrors facing each other perfectly parallel, separated by some fixed distance, say a meter. Between them a single pulse of light bouncing back and forth, up to the top mirror, down to the bottom, up again, down again. Each round trip is 1 tick. It's a perfectly valid clock. Light travels at a known, fixed speed. The distance is fixed, so each tick takes a precise and predictable amount of time. Now imagine that clock is sitting still right in front of you. You watch the light pulse travel straight up and straight down. Simple, clean. Each tick is identical. Now imagine the same clock moving sideways at tremendous speed. Not quite the speed of light, but a significant fraction of it. You are watching it pass. From your perspective, the light pulse no longer travels straight up and down. It can't, because the clock itself is moving sideways while the pulse travels. So the pulse must trace a diagonal path, up and to the right, then down and to the right, a long, shallow triangle with each tick instead of a short, straight line. The pulse travels a greater distance to complete each tick. Here is the constraint that changes everything. The speed of light cannot change. It is always the same. If the pulse must travel a longer path to complete one tick, but it cannot travel that longer path any faster, then each tick simply takes more time. Not because of any mechanical defect, not because of vibration or wear, but because of the geometry of the situation, because of the deep structure of reality. This is not a thought experiment that stays safely in the realm of imagination. It has been measured directly and repeatedly in the world we actually live in. High in the atmosphere, roughly 15 kilometers above the surface of the Earth, cosmic rays, high-energy particles arriving from deep space, collide with molecules of air and produce showers of secondary particles. Among those particles are muons, which are something like heavy cousins of electrons. A muon at rest has a natural lifetime of about 2 microseconds, 2 millionths of a second, before it decays into other particles. That is not very long. Even traveling at nearly the speed of light, a muon with a 2 microsecond lifetime should only cover about 600 meters before it vanishes. Yet muons produced 15 kilometers up reach the surface of the Earth in vast numbers. They should not be able to. The distance is roughly 25 times too great for their brief lives to cover, even at the highest possible speed. The explanation is time dilation. These muons are traveling at speeds very close to the speed of light, roughly 98% of it. At that speed, the time dilation effect stretches their apparent lifetime, from our perspective on the ground, by a factor of about 5. A particle that would decay in 2 microseconds at rest survives for 10 microseconds as we observe it hurtling toward us, and 10 microseconds at nearly the speed of light is enough to cover 15 kilometers. The muons arrive because their clocks are running slowly relative to ours. They are, in a precise and literal sense, living longer from our point of view than they would if they were sitting still. There is a beautiful symmetry here worth pausing over. From the muon's own perspective, its clock is running perfectly normally. It still lives for 2 microseconds by its own reckoning. What has changed from the muon's frame is not time but distance. The 15 kilometers of atmosphere has been compressed, shortened by the same relativistic effect, so that the journey is brief enough to complete in its short lifetime. The first experimental confirmation of this velocity-driven time dilation that didn't rely on cosmic particles came in 1938 from 2 physicists named Herbert Ives and G.R. Stilwell. They fired hydrogen atoms along a tube at high speed and measured the frequency of the light those atoms emitted, the precise color of the light, which acts like a natural clock, a fixed number of oscillations per second. When the atoms were moving fast, the frequency of their emitted light shifted in a way that could only be explained by the atom's internal clocks running slowly. The shift matched Einstein's prediction to within 1%. It was a quiet, careful, precise confirmation. Time genuinely runs differently for things that are moving. What this means for anything traveling at a significant fraction of the speed of light is worth sitting with for a moment. Not just clocks, not just muons or hydrogen atoms. Every process, every heartbeat, if a heart were somehow there, every thought, every chemical reaction, every decay of every atom. All of it slows in perfect lockstep. There is no way to feel the slowing from inside, because every internal reference you have is slowing at exactly the same rate. You would feel entirely normal. Your watch would tick normally. Your coffee would cool at its usual pace. Only when you compared notes with someone who had been sitting still would you discover that less time had passed for you. that you had aged less, lived less, experienced less elapsed time than the person you left behind. Time is not a backdrop, it is a dimension, and like all dimensions, it can be stretched. Speed is one way to slow a clock, but there is another way, deeper and stranger, and it operates all around us all the time, so quietly that we never feel it. Gravity bends time. Einstein spent the decade after his 1905 paper on special relativity working on a harder problem. Special relativity described what happened when things moved at constant speeds relative to each other. But what about acceleration? What about gravity? How did those fit into the picture? The insight that unlocked it came to him in 1907, and he later described it as the happiest thought of his life. He imagined a person in a closed box with no windows. If that box were sitting on the surface of the earth, the person inside would feel their weight pressing them toward the floor. If the box were instead accelerating upward through empty space, far from any planet or star, the person would feel exactly the same thing, their weight pressing them toward what was now the bottom of the box. There was no experiment they could perform from inside to distinguish between the two situations. Gravity and acceleration were not merely similar. They were, in some deep sense, the same thing. From this insight, Einstein spent 8 more years building a complete mathematical description of gravity, one of the most demanding intellectual undertakings in the history of science. What emerged in 1915 was his general theory of relativity, and its central claim was extraordinary. Gravity is not a force in the way Newton had described it. Gravity is the curvature of space-time. A massive object, a planet, a star, doesn't reach out and pull things toward it. Instead, it warps the fabric of space and time around it, the way a heavy stone resting on a stretched rubber sheet creates a depression. Everything nearby, light, matter, and time itself, follows the contours of that warped geometry. What we feel as the pull of gravity is simply the natural tendency of things to follow the curves in space-time. And in a curved space-time, time runs differently depending on where you are. Deeper in a gravitational field, closer to the massive object, where space-time is more tightly curved, a clock ticks more slowly. Higher up, where the curvature is gentler and gravity's grip is weaker, a clock ticks faster. Near the surface of a neutron star, an object packing more than the mass of our sun into a sphere about 20 kilometers across, time runs noticeably slower than it does far away. Near a black hole, as we'll explore later, the effect becomes almost incomprehensible. But the effect is real even in the mild gravity we experience every day. Picture 2 identical clocks, both perfectly calibrated, both keeping exactly the same time. You place one at the base of a tall building and carry the other to the top. The clock at the base sits slightly deeper in Earth's gravitational field than the one at the top. The difference in gravitational pull between the two heights is tiny. Earth is large and the building is a small fraction of Earth's radius, but it is not zero. And so the clock at the base, sitting in the very slightly stronger gravitational field, ticks very slightly more slowly than the one at the top. Over the course of a day, the difference is measured in billionths of a second. You would never notice it. But it is real. And it was confirmed with extraordinary precision in 1959 by 2 physicists at Harvard, Robert Pound and Glenn Repka. Their experiment was elegant in its simplicity. They used gamma rays, very high-energy light, produced by radioactive iron atoms. Gamma rays, like all light, have a specific frequency, and that frequency acts as a precise clock. Pound and Repka sent gamma rays from the top of a tower at Harvard down to a detector at the bottom, a vertical distance of just 22 meters. As the gamma rays fell through that 22 meters, they were moving into a slightly stronger gravitational field. According to general relativity, clocks run slower in stronger gravitational fields, and the frequency of light is a kind of clock. So the frequency of the gamma rays should shift as they descended. The shift was tiny. It was equivalent to a change in frequency of about 2 parts in 10 to the power of 15, a number so small it strains description, like noticing a single extra grain of sand on a beach. But Pound and Rebka's apparatus was sensitive enough to measure it, and it matched Einstein's prediction exactly. 22 meters. The height of a modest building, and in that modest distance, time itself was measurably different at the top than at the bottom. The universe was not keeping a single clock. It never had been. Every point in space, every altitude, every depth in a gravitational field had its own slightly different rate of time, all of them ticking away in their own quiet rhythm, none of them wrong, none of them more real than the others. Einstein had not just described gravity. He had revealed that the passage of time is woven into the very shape of space, and that shape is not flat. It was never flat. It curves around every grain of matter in the universe, and time flows differently through every curve. October 1971. The world was busy with other things. A war was ongoing in Southeast Asia. The first microprocessors were being designed in California. And in Washington, D.C., 2 physicists named Joseph Hafele and Richard Keating were doing something that must have seemed, to the other passengers around them, entirely ordinary. They were boarding commercial flights. They were settling into their seats. Their luggage, however, was unusual. Tucked carefully into the seats beside them were 4 cesium atomic clocks, devices that keep time by counting the oscillations of cesium atoms, oscillations so regular and so rapid that these clocks could measure differences in elapsed time down to billionths of a second. Hafele and Keating were going to fly those clocks around the world and see if Einstein was right. The experiment had been proposed simply and directly. Einstein's theories made specific, calculable predictions. A clock moving faster than a reference clock should run slow due to velocity-driven time dilation. A clock sitting higher in Earth's gravitational field should run fast due to gravitational time dilation. An airborne clock experienced both effects simultaneously. It was moving faster than the ground clocks aboard the aircraft, which should slow it, and it was sitting at altitude in a weaker gravitational field, which should speed it up. The 2 effects worked in opposite directions, and the question was which one won, and by exactly how much. There was a further complication. The Earth itself is rotating. A clock flying eastward, in the same direction as Earth's rotation, is moving faster relative to the distant stars than a clock sitting on the ground because it is adding its airspeed to Earth's rotational speed. A clock flying westward is moving slower relative to the stars because it is flying against Earth's rotation, partially subtracting from it. So the velocity-driven time dilation would be different for the 2 directions of travel, and the gravitational effect, depending on the precise altitude of each flight, would also vary. Hafele and Keating flew their clocks eastward around the world on one journey, then westward on another, logging the precise flight paths and altitudes, and then returned to Washington to compare their traveling clocks with the reference clocks that had been sitting, patient and still, at the United States Naval Observatory. The results were precisely what Einstein's equations predicted. The clocks that had flown eastward came back running slightly slow. They had aged less than the ground clocks, because the velocity effect had slightly dominated the gravitational effect for eastward flight. The clocks that had flown westward came back running slightly fast. They had aged more than the ground clocks, because at lower effective speed relative to the stars, the gravitational effect had dominated, and the 2 sets of traveling clocks differed from each other, not just from the ground clocks. The numbers were small, measured in tens to hundreds of nanoseconds, billionths of a second, but they matched the theoretical predictions with a precision that left no room for doubt. Time had genuinely passed at different rates for the clocks on the planes than for the clocks on the ground. Einstein had been right, not just in principle, but in the specific numbers. What makes this experiment so quietly remarkable is its ordinariness. These were commercial flights. The clocks sat in passenger seats. The physics of the universe was being confirmed somewhere between the drink trolley and the window view. It was not a particle accelerator or a space telescope. It was a Tuesday afternoon over the Pacific Ocean. The practical descendant of that experiment now orbits the Earth in the form of the Global Positioning System, the network of satellites that your phone consults whenever it needs to know where you are. Those satellites carry atomic clocks of their own, and they orbit at roughly 14,000 kilometers per hour, considerably faster than anything on Earth's surface. They also orbit at an altitude of about 20,000 kilometers, where Earth's gravitational field is considerably weaker than at the surface. Both effects are in play. Because the satellites are moving so fast, their clocks run slow by about 7 microseconds per day. That is the velocity effect. Because the satellites are so high up, in weaker gravity, their clocks run fast by about 45 microseconds per day. That is the gravitational effect. The net result is that GPS satellite clocks run fast by roughly 38 microseconds every day compared to clocks on the ground. 38 microseconds might sound trivial, but GPS works by measuring the time it takes signals to travel from satellites to your phone, and timing errors translate directly into position errors. Light travels about 11 kilometers in 38 microseconds. If the satellite clocks were not continuously corrected for relativistic effects, the position errors would accumulate at roughly 11 kilometers per day. Within a week, GPS would be useless for navigation. Every time you ask your phone where you are, it gives you an answer that is only accurate because the engineers who built the system took Einstein seriously. There is something deeply satisfying about that. The most abstract and seemingly impractical idea in physics, that time is relative, that clocks in different gravitational fields and at different speeds tick at different rates, turns out to be not abstract at all. It is embedded in the infrastructure of daily life, quietly corrected for every few seconds so that you can find a coffee shop in an unfamiliar city. In 2022, scientists at an American government laboratory called the National Institute of Standards and Technology published a result that was, in its own quiet way, one of the most remarkable measurements in the history of physics. They had measured gravitational time dilation across a distance of 1 millimeter. Not 1 kilometer, not 22 meters, like the Harvard Tower experiment. 1 millimeter, the width of the tip of a pencil, the thickness of a credit card, a distance so small that you could cross it by pressing 2 fingernails together. To understand how that was possible, it helps to understand the kind of clock they were using, because it was not anything like the clocks you have in your home, and not even much like the cesium clocks that flew around the world in 1971. The clocks used in this experiment belong to a category called optical lattice clocks. The name describes their construction. A cloud of atoms, in this case, atoms of ytterbium, a soft silvery metal, is cooled to a temperature almost unimaginably close to absolute zero, the coldest temperature that physics permits, where the thermal jostling of atoms slows almost to nothing. Then, intersecting laser beams are arranged so that their interference patterns create a kind of microscopic three-dimensional grid, a lattice made of light, and individual atoms are held almost perfectly still within the nodes of that lattice, like marbles resting in tiny invisible cups. This is the optical lattice. Each atom in that lattice has a natural oscillation frequency, a rate at which its electrons cycle between energy levels, absorbing and releasing light at a very specific wavelength. This oscillation is extraordinarily stable, far more stable than any mechanical vibration, and it serves as the clock's tick. The clock measures time by counting those oscillations. How precise are these clocks? They are accurate to better than 1 second's error in 30 billion years. The universe itself is only about 14 billion years old. These clocks are so precise that if 2 of them had been started at the moment of the Big Bang and run continuously until now, they would still agree with each other to within a second. With clocks this sensitive, the NIST team was able to do something that would have seemed impossible even a decade earlier. They prepared a single cloud of ytterbium atoms, cooled and held in their optical lattice, and they divided that cloud into 2 layers, one layer sitting just 1 millimeter above the other. Then they compared the tick rates of the atoms in the upper layer with the tick rates of the atoms in the lower layer. The upper atoms, sitting 1 millimeter higher in Earth's gravitational field, were in ever so slightly weaker gravity, and in ever so slightly weaker gravity, their clocks ran ever so slightly faster. The difference was real, and it was measured. It matched what general relativity predicted. 1 millimeter. Within a single cloud of atoms, time was flowing at different rates at the top and the bottom of a space smaller than a raindrop. Physicists often reach for a particular image when they want to make this personal, and it is an image worth holding gently as you rest tonight. Your feet are closer to the center of the earth than your head. The difference in height, for most people, is somewhere between 1.5 and 2 meters. That means your feet sit in a very slightly stronger gravitational field than your head. And in that very slightly stronger field, your feet's clocks, every atom, every cell, every biological process, tick very slightly more slowly. Your head is aging faster than your feet. Not by an amount you could ever feel or measure without instruments of extraordinary sensitivity. In the course of a human lifetime, the difference amounts to a tiny fraction of a microsecond. But it is real. It has been measured. The NIST experiment confirmed that the effect is genuine even across 1 millimeter, and your body spans roughly 2,000 millimeters from foot to crown. You are not a single clock. You are a gradient of time, slightly faster at the top than at the bottom, your whole body, a tiny living demonstration of a principle that governs the largest structures in the universe. There is something almost tender about that, something that makes the universe feel less distant and more intimate. The same physics that governs the warping of space-time around a star is happening right now, within the space of your own body as you lie still in the dark. The NIST experiment also points toward the future of fundamental physics. Clocks this precise are sensitive enough to detect not just the gravitational field of the Earth, but potentially tiny variations in that field. Variations that might reveal the presence of underground structures or help map Earth's interior, or even, some physicists hope, detect the influence of dark matter, the invisible substance that makes up most of the mass of the universe, but has so far resisted every attempt to observe it directly. Time, measured with enough patience and precision, becomes a probe of the deepest structure of reality. The second, it turns out, is not a fixed and featureless unit. It is a window. There is a puzzle that has followed special relativity since almost the moment it was published, and it goes like this. Suppose you have 2 twins. One stays at home. The other boards a spacecraft, travels at a significant fraction of the speed of light to a distant star, turns around, and comes back. When they meet again, the traveling twin has aged less. Their clocks ran slowly during the journey, and when they return, they are measurably younger than the twin who stayed behind. This much follows directly from what we've already explored, but here is the puzzle. If motion is relative, if there is no absolute reference frame, no fixed background against which to measure who is really moving, then why can't the traveling twin claim that it was the stay-at-home twin who moved away and came back? If motion is symmetric, shouldn't both twins be younger than the other when they meet? And since that's impossible, what breaks the symmetry? The answer lies in something that special relativity treats very carefully: acceleration. The stay-at-home twin floats in space, undisturbed, in a single inertial frame, a frame of reference moving at constant velocity. The traveling twin does not. To go to the star and come back, they must accelerate away from Earth, decelerate as they approach the star, turn around, accelerate again toward home, and decelerate to land. Each of those phases involves a change in velocity, a change in direction, a change in frame of reference. The traveling twins' journey is not symmetric, with the stay-at-home twins waiting because one of them changed frames and the other did not. That asymmetry is real, and it resolves the apparent paradox. Only the traveler ages less. This is not just a thought experiment. In 2015 and 2016, NASA astronaut Scott Kelly spent nearly a year, 340 days, aboard the International Space Station, while his identical twin brother Mark Kelly remained on Earth. The station orbits at roughly 28,000 kilometers per hour, and at an altitude of about 400 kilometers per hour, and at an altitude of about 400 kilometers. Both relativistic effects were in play. Scott's high speed tended to slow his clock, while his slightly higher altitude in weaker gravity tended to speed it up. The velocity effect dominated, and when Scott returned to Earth in March 2016, he had aged approximately 5 milliseconds less than Mark. 5 milliseconds, about the time it takes to blink divided by 100. Not perceptible in any human sense, but real and confirmed. What made the Scott and Mark Kelly study particularly rich was that NASA took the opportunity to study the twins biologically, not just physically. The results were published in 2009 and were more complex than anyone had expected. Scott's telomeres, the protective caps at the ends of chromosomes, which tend to shorten as cells divide and age, had actually lengthened during his time in space. Telomere lengthening is associated with various cellular stresses, including radiation exposure, and the station's altitude places it outside much of Earth's protective magnetic field. When Scott returned to Earth, his telomeres shortened again, partly recovering toward their pre-flight length. The biological picture was complicated by factors beyond time dilation: radiation, microgravity, the psychological and physical demands of spaceflight. But the study confirmed that a year in space leaves measurable traces in the body's aging machinery, and that the two brothers, genetically identical at birth, had diverged in small but measurable ways by the time Scott's boots touched Earth again. Now consider what time dilation would mean at far greater speeds. Not the 28,000 kilometers per hour of the space station, but something approaching the speed of light itself, say 90% of it, or 99%. At 99% of the speed of light, time dilation becomes dramatic. A clock moving at that speed ticks about 7 times more slowly than a stationary one. At 99.9%, the factor is more than 22. At 99.99%, it exceeds 200. For a traveler moving at these speeds, the experience would be completely normal from the inside. Their heartbeat, their thoughts, their metabolism, all slowing in perfect lockstep with the clock so that nothing feels different. They would eat their meals at the usual hours, read their usual hours, read their usual hours. But outside the ship, centuries might be passing. A journey to a star 4 light-years away at 99% of the speed of light would take about 4 years and a few months by the traveler's reckoning, but more than 4 years by Earth's calendar, and if the speed were higher still, the gap would widen enormously. The traveler would return to find the world had moved on without them, not through any failure on their part, not through any strange sensation during the journey, but simply because time, like the river it was once imagined to be, flows at different rates in different places, and they had spent their time in a faster current, arriving at a downstream that everyone else reached years or decades earlier. There is something both wondrous and quietly melancholy in that image. To travel fast is to age slowly. To return is to find the world further along its own journey than you are along yours. Somewhere in the universe tonight, in most galaxies, including our own, there are objects so extreme that the physics we have been exploring gently all evening reaches its outer limit and begins to strain against something it cannot yet fully describe. A black hole begins as a star, not just any star, a massive one, at least several times the mass of our sun, burning with the fierce brightness that comes from fusing lighter elements into heavier ones deep in its core. For millions of years, that fusion generates an outward pressure that balances the inward pull of the star's own gravity. The star is a negotiation between two forces, held in a kind of equilibrium, shining steadily. But stars are not eternal. The fuel runs out. When the core of a massive star exhausts its supply of fusible material, the outward pressure fails. In less than a second, sometimes in a fraction of a second, the core collapses inward. The outer layers, falling inward and then rebounding in a colossal explosion called a supernova, are blasted into space. And the core, if it is massive enough, has nothing left to stop its collapse. It falls inward past the density of ordinary matter, past the density of neutrons packed together as tightly as physics permits, and into something for which our everyday intuitions have no preparation. The resulting object is so dense and its gravitational field so intense that it warps space-time around it with an extreme that Einstein's equations describe but that the human mind struggles to hold. At a certain distance from the center, a boundary called the event horizon, the curvature of space-time becomes so severe that the escape velocity, the speed you would need to travel to escape the gravitational pull, reaches the speed of light. And since nothing can travel faster than light, nothing can escape from within that boundary. Not matter, not radiation, not information of any kind. The event horizon is not a physical surface. There is nothing to touch, nothing to feel as you cross it. It is simply a point of no return, a boundary in the geometry of space-time, beyond which all paths lead inward. Now consider what time dilation looks like in this extreme environment. Imagine watching a clock falling toward a black hole from a safe distance. As the clock approaches the event horizon, it is moving deeper and deeper into an increasingly intense gravitational field. From your distant perspective, its ticking slows. The light it emits becomes stretched. Its wavelength grows longer, shifting from visible light toward infrared, toward radio waves, its color deepening toward red and then beyond. This stretching of light's wavelength due to gravity is called gravitational redshift, and it is the visual signature of time slowing down. The clock's ticking slows and slows, its light growing dimmer and redder, until, as it approaches the horizon, it appears to freeze. The last image of the clock seems to hover there at the boundary, suspended, its final moment stretched across all of future time. From the perspective of the clock itself, however, nothing unusual happens as it crosses the horizon. The infalling observer feels no jolt, no boundary, no sensation of crossing a threshold. Their own time flows normally. They pass through the event horizon and continue inward. It is only later, in a time that may be very brief, depending on the size of the black hole, that they reach the center, the singularity, where the density of matter becomes, in the mathematics of general relativity, infinite, and the theory itself breaks down. A singularity. The word means a point at which a mathematical description ceases to give finite answers, is where general relativity admits it has reached its own edge. The equations produce infinities, and infinities in physics are almost always a sign that the theory is being asked a question. Something else is needed, something that does not yet exist in complete form. That something is a theory of quantum gravity. General relativity describes the large-scale structure of space-time with extraordinary accuracy. Quantum mechanics, the theory describing the behavior of atoms and subatomic particles, describes the small-scale world with equally extraordinary accuracy. But the two theories are, at a deep mathematical level, incompatible. They rest on different foundations, use different languages, and produce contradictions when applied simultaneously to the same extreme environment. A singularity is exactly such an environment, infinitely small, infinitely dense, where both gravity and quantum effects are simultaneously crucial. One of the places this tension becomes vivid is in what physicists call the information paradox. In quantum mechanics, information, the complete description of the state of a physical system, is never truly destroyed. It can be scrambled, transformed, spread across many particles, but it persists. Yet general relativity, applied to black holes, seems to say that anything falling past the event horizon vanishes from the universe forever. Its information is gone. These two claims cannot both be right. Something in our understanding is incomplete. Stephen Hawking worked on this problem for decades, and in 1974 he showed, using a calculation that combined quantum mechanics with the curved spacetime of general relativity, that black holes are not perfectly black. They slowly emit a faint thermal radiation, now called Hawking radiation, after him. This radiation carries energy away from the black hole, causing it to slowly evaporate over astronomical timescales. But whether that radiation carries the information of everything that fell in, and how, remains one of the deepest unsettled questions in physics. What time means at the very center of a black hole, at the singularity, is genuinely unknown. Our best theory says that the concept of time, as we understand it, may not apply there in any recognizable form. Whether time has a beginning, an end, a direction, a rate, all of these become uncertain at that extreme. The singularity is where the story of time, as we have been tracing it tonight, reaches a place it cannot yet describe. And perhaps there is something restful in that. Not every question needs an answer tonight. Some of the most beautiful things about the universe are the places where our understanding softens at the edges, where the known gives way to the vast unknown, and where the darkness ahead is not emptiness but depth. We have come a long way tonight, from a Swiss patent office and a question about riding alongside light, through the careful measurements of physicists carrying clocks aboard aeroplanes, through the millimeter-scale precision of atoms cooled almost to stillness, to the edge of everything where time itself loses its familiar shape. It is a long journey, and you have been drifting through it gently, half hearing it the way you half hear rain. Let it settle now, not as a set of facts to remember, but as a feeling about the world. Time is not a fixed river. It never was. It bends and pools and thins, depending on where you are, how fast you move, how deep you sit in the gravitational field of the nearest massive body. Every person on Earth is aging at a very slightly different rate. People living at high altitude age a fraction faster than those near sea level. People near the equator move a little faster through space, with Earth's rotation and age a fraction slower. People in aeroplanes are somewhere in between. None of these differences are large enough to feel. None of them will show up in a mirror or a birthday cake, but they are real, and they have been measured, and they are happening right now, all across the surface of this planet, in the lives of every person asleep and awake. Think again of that NIST cloud of atoms in 2022, a single cloud, barely visible to the naked eye, cooled to a whisper above absolute zero, its upper atoms ticking fractionally faster than its lower ones across 1 millimeter of height, time flowing at different rates within a space smaller than a raindrop. There is no better image for what the universe actually is, not a stage with a single, universal clock ticking in the wings, but a vast, intricate, continuously varying field of time, every point in it subtly different from every other, all of it woven together into what we experience as the ordinary, continuous passage of a day. And then there is the human version of this, the version that is harder to measure but no less real. You have felt time move differently at different moments of your life. A childhood summer, long days, no particular destination, the hours filled with small things, can seem, in memory, to have lasted longer than entire years of adult life. An anxious hour in a waiting room stretches like taffy, each minute pulling out past its natural length. A peaceful afternoon, a conversation with someone you love, a walk somewhere beautiful. These seem to compress, to pass before you've had time to fully inhabit them. Physics has not explained this. The subjective elasticity of time, the way attention and emotion stretch and compress our inner sense of its passage, is a question for neuroscience and psychology, not for general relativity. But there is something quietly resonant in the parallel. The universe we live in has time dilation woven into its fabric at every scale, from the cosmological to the subatomic. And our experience of time, whatever its biological underpinnings, echoes that flexibility. We are not clocks. We have never been clocks. We are something more porous and variable than that. Creatures whose inner experience of duration shifts with circumstance, with mood, with the quality of our attention. Einstein once said, or is often said to have said, the attribution is somewhat uncertain, that when you sit with a beautiful person for an hour, it feels like a minute, and when you sit on a hot stove for a minute, it feels like an hour. He was joking, but the joke points at something true. Our perception of time is not a passive recording of an objective flow. It is shaped by everything we are bringing to the moment, by whether we are anxious or calm, by whether we are engaged or waiting, by whether we are, as you perhaps are now, drifting towards sleep. Sleep is its own relationship with time. In deep, dreamless sleep, there is no time at all, or none that we can access afterward. You close your eyes, and the next thing you know, it is morning. Hours have passed in what feels like no time, because there was no subjective experience to fill them. And in dreams, time does something else entirely. It becomes non-linear. It folds back on itself. It allows you to be in two periods of your life simultaneously, to revisit things that happened decades ago with the vividness of the present moment. The dreaming mind has its own relationship with duration, one that bears no particular resemblance to the clock on the wall. Perhaps all of this, the physics and the phenomenology, the measured and the felt, points toward the same underlying truth, that time is not a thing we are subject to exactly. It is more like a medium we move through, and the way we move through it shapes how it flows. Speed matters. Position matters. Gravity matters. Attention matters. The quality of the present moment matters. Somewhere above you, GPS satellites are having their clocks corrected right now, adjusted for the 38 microseconds per day by which relativity has bent their timekeeping. Somewhere in the deep sky, a clock is falling toward an event horizon, its light stretching redder and dimmer, its final moment apparently frozen at the boundary between the known and the unknown. And here, in this room, in this body, in the millimeter between the top of your head and the bottom of your skull, time is flowing at its own quiet gradient, fractionally faster at the crown, fractionally slower at the base. The whole of you a gentle demonstration of a principle that governs the largest and the smallest things the universe contains. You have been here for all of it. You have been floating on this river your entire life, and the river has been bending around you, and you have aged at exactly the rate the universe arranged for you, given where you were and how you moved and how deep in the gravity of this world you chose to rest. That is enough. That is more than enough. The day behind you has already grown distant. The questions it carried have no urgency now. The universe is patient and old, and it has been keeping its own time since long before anyone was here to notice. You don't need to hold any of this. You don't need to carry it forward. The words will dissolve the way all things dissolve in the dark, and what remains will be quieter than thought. Somewhere a clock is ticking more slowly. Somewhere time is pooling in a curve of space-time, deep and still. And here, in the soft gravity of this night, your own clock is doing exactly what it should. Drift now, if you're ready. Sleep well,